I'm Steve Comrush from Colorado State University, and I'll be presenting SequenceR, sequence-to-sequence learning for end-to-end program repair, originally published in Transactions on Software Engineering. One-line commits are a common bug fix representing about 10% of the commits in GitHub, and SequenceR has been trained to learn a variety of techniques for repairing these type of bugs. For example, call deletion is a case where two method calls might be used in a Java line, and the correct fix is to delete one of the two calls. Argument addition is a case where an extra argument might be needed in a method call. And SequenceR has learned how to produce these two different types of repairs, as well as a variety of other ones, which can be read about in our paper. The sequence-to-sequence model is a system which takes an input language as a set of tokens and can translate into an output language as a set of tokens. It uses a hidden state, and it learns how to embed the input sequence into its hidden state, which is then used to generate the output sequence using another learned set of weights. This whole system can be trained using thousands or millions of examples of input sequences and correct output sequences. So for SequenceR, we're learning to translate from buggy code to fixed code. And an example of buggy code is shown on the left, where we have an entire class and a buggy method increment, which is returning bar-1. We create an abstract buggy context where we remove code from methods which are not buggy, and we identify the buggy line with a start bug end bug token. The buggy line might be identified through fault localization, which is taught in other papers. We also deal with the large vocabulary problem in Java, which is caused by people creating a variety of names for both variables and methods. And when a token is outside of the learned vocabulary, it is identified with the unknown token. However, we have a copy mechanism which allows tokens from the abstract buggy context to still be used in the output fixed line. The way we train our model is to mine GitHub and find a variety of actual human commits that presumably change buggy source code by only one line and create a fixed line for that bug. And we train SequenceR by updating the parameters using backpropagation so that the sequence-to-sequence network learns how to translate buggy code into fixed code. Our use model is to take cases where you have a test failure in your project, you run fault localization, and given a buggy line identified, you create the buggy context abstraction, and the sequence-to-sequence network is then used to generate a patch which can be validated before humans are involved in the loop to approve the fix. Now, the details of our model, it's a fairly advanced sequence-to-sequence network using LSTMs, and the encoder is shown in yellow, which creates an embedding for the abstract buggy context. The decoder is shown in green, which uses the embedding to create the predicted fixed line. And the copy mechanism and its components are shown in orange, which allows the decoder to pay attention to the states that occurred when the abstract buggy context was processed and potentially copy tokens from the abstract buggy context. So this is how we deal with the unlimited vocabulary issue. And this slide describes that in more detail. Our first line here shows that with a 50,000 word vocabulary but no copy mechanism, beam size of 1, we got 55 out of 4,700 test cases correct. When the beam size is 50, we jumped by almost 4x, and that meant that there were 50 possibilities generated by the model. When we dropped to 1,000 word vocabulary, but we enabled the copy mechanism, which allows the system to copy code, in this case, simply from the buggy line, we got up to 826 passing cases. Now, these first three are all based on just the buggy line being input and the fixed line being output. When we included the abstract buggy context, now we got to a full 950 passing cases. And that allows the copy mechanism to not just look at the buggy line as input, but the whole buggy method and even the buggy class in some cases. We also evaluated sequence R on defects for J, which is a common data set that other papers have used. And of the 75 bugs which are repairable with single line fixes, we found 19 that had plausible patches. That is, patches that passed all of the test cases provided. And 14 of those 19 were the correct fix. So in the case where the 5 plausible patches did not actually fix the bug, those would be indicative of potentially a hole in the test suite. So all 19 of those, which could be found automatically, are potentially interesting from a software engineering. In the end, Sequence R is the first system that generates compilable test-verified patches based on neural machine translation. It finds the correct patch for over 20% of the test data, and it was able to fix 14 out of 75 bugs from defects for. Thank you very much.